everybody. We're going to go through the 3.1 notes on uniform circular motion. So uniform circular motion describes an object that travels around a circle at a constant speed around an external axis. We call that uniform circular motion. So things could be, we could have a moon that's orbiting in a circle around a planet. The planet would be that external axis. We'll talk a lot about like a ball on a string that's traveling in a circle, where this is that external axis. Maybe a car that's driving around a bend. There's some center of that circle that we're driving around, so that would be that external axis. We'll look at rotating objects in Unit 6. We analyze those a little bit differently, where the whole object itself is rotating instead of just something moving in a circle. Cool. So let's draw on this circle over here. So let's say we have an object that is rotating, or not rotating, it is moving in a circle around some center point. Okay. So this is the center of our circle. The distance that this object is away from the center is r, that's the radius. And so we've got an object out here. Let's say that we're going in a circle in this direction. At this point right here, at this instant, the velocity would be tangent to the circle or perpendicular to the radius at this point. So my velocity would be in this direction. If I was up here, my velocity would be this direction, and so on. So at different points around the circle, even if I'm going the same speed, the direction is changing. And so remember, velocity is a vector. It has a magnitude, so that's an amount, and a direction. To change the velocity, even if we're not changing the speed, there needs to be some sort of force to cause this object to move in a circle. Because it wants to move in a straight line, we have to force it to move in a circular path. So that's going to be first thing I want you to take a note of down here. That velocity is tangent to the path. So it's perpendicular. If we were to draw a radius, it's perpendicular to that path. And if I think about, maybe I draw this object instant later, right here, the velocity be going in this direction. If I was to look at the difference in those velocities, I would find that it's being pushed towards the center. So at each of these points, it's actually being pushed or accelerated towards the center of the circle. So that change in velocity points towards the center, which means so does the force and the acceleration. So let's define a few things. First one is centripetal acceleration. That's going to point towards the center. And I'm going to give you a new equation for centripetal acceleration. It's going to be a capital or lowercase a with a c subscript for centripetal. And it equals our speed squared divided by our radius. So v is our speed in meters per second. R is the radius in meters. Where there's acceleration, there is a force. So let's define centripetal force. Centripetal force has to be caused by a known force, like friction or tension or gravity. Something has to be pushing or pulling on this object. We're never going to label a centripetal force on its own. So we're going to still look at the sum of forces in the centripetal direction, but you should never label Fc on a diagram or have it in an equation. We're going to replace Fc with tension or friction or whatever is there. It's going to be mass times our centripetal acceleration. It's still just Newton's second law, just with a little c here. Usually what we'll do is just combine these two equations. So substitute AC in, and we'll get Sum of forces in the centripetal direction is mv squared over r. All right, and then our last definition is going to be a period. This is a time measurement. It's the time for one revolution. It's a capital T. And the equation that we'll use for capital T is distance. Distance around a circle is the circumference, which is 2 pi r, over the speed. Let's do an example. A car travels around a circular turn at 18 meters per second. The radius is 45 meters. So that looks like is, here we have a car. So we're looking from above. It is traveling at 18 meters per second. The radius is 45 meters. The centripetal acceleration, A, is v squared over r. So that is 18 squared over 45, which is 7.2 meters per second squared. We're going to draw the free body diagram. So here's our car. Let's say we're looking from behind. So there are our wheels. It's traveling away from us. We have the weight of the car. We have some normal force. And this car wants to be traveling in a straight line. The reason it doesn't is because of friction between the tires and the road. Imagine like if you hit a patch of ice, you might just keep sliding straight because you lose that friction. But to turn to the left here, we need to have friction pulling us in. Part C, if we have this coefficient of friction, what's the maximum speed we can travel? So we want to look at sum of forces in the centripetal direction equals mv squared over r. I want to look here, my sum of forces in the centripetal direction. Okay? I'm going to look at what forces are towards the center of my circle. Okay? That's going to be the force of friction. Okay? I don't have normal force and the weight. Those are not pointed towards or away from the circle. So that's going to be force of friction equals mv squared over r. Force of friction is mu times the normal force. Here I'm on a flat road. My normal force is equal to the weight. So mu mg equals mv squared over r. You can cancel out the m's. And then we're going to plug in what we know and solve for v. So mu is 0.55, 9.8 for g equals v squared over 45. Rearrange that and solve it, and we should get v equals 15.6 meters per second. One thing I forgot to mention real quick, centripetal force. It's going to be positive if it's towards the center, negative if it's away from the center.